the decibel equation. Okay. So we had talked about the fact that the amplitude of the sound wave is related to the energy. So let me go in and kind of recall that the energy for a simple harmonic oscillator is proportional to the amplitude squared. And when you shake the string in simple harmonic motion, you create harmonic waves. And so because of this, you get that the energy transported by a wave, and that's what waves do, is they transport energy, is proportional to the amplitude squared. Okay. And then what we found was that our intensity was the average power per area of our waves, where the power is the energy per time. So this would be our, energy per time per area. So this A is the area, but this A is the amplitude. Yeah, I know. I don't know why there aren't more symbols. Okay. And what we get is that the bigger the intensity of a wave, if it's a sound wave, then the louder it will be. And if it's a light wave, the brighter it will be. And so that was what we had established, except for our sounds. The intensity for the threshold of hearing was our 1 times 10 to the minus 12 watts per meter squared, was the softest sound that we can hear. And then this went up to the threshold of pain. And now it goes beyond this. I mean, I always worry that this implies this is the top value, but it is not. So the threshold of pain is at, 1 times 10 to the 0 watts per meter squared, 1. And so there are 12 orders of magnitude where the difference between the softest sound we can, normal healthy human ears can hear, to where it's painful for the sounds to listen to. Now the intensity goes on higher than that. I mean, you can just, rapidly damage your hearing. You can actually, rend things, break things apart with higher and higher intensity pressure waves. But yeah, this is usually how high we talk about it in terms of, just remaining as sound at that stage. Okay. And so 12 orders of magnitude is very difficult to envision. Our brains just don't really readily picture things that are that different in magnitude. So then this is why we incorporated what they call the decibel equation. They use this symbol, which is the second Greek letter called beta. Hence we get alpha, beta, gamma, delta, we get the alphabet. We talked about the fact that when you do the Bell scale, then it would go from 0 to 12, because it's the orders of magnitude explicitly, from 0 to 12 kind of things. But then they thought that was too coarse. We went from something that was so fine I can't picture it, from 1 meter, like waist high, to the distance from the sun to Jupiter. I mean, we can't picture 12 orders of magnitude where the difference in any reasonable sense. Then we did the common logarithm, or the Briggsian log, of the intensity over that reference intensity, which is the threshold of hearing. So this letter is beta, lowercase one. This is what they refer to as the intensity level. You have to be really careful with the names, with the nomenclature here. Because the I is our intensity. So intensity level. I mean, so we gotta be careful. with these. They're easy to mix up. This I naught is the reference, which is our threshold of hearing. So that's this 1 times 10 to the minus 12 watts per meter squared. The times 10 is because we're in the decibel scale to tenths of bells. And so that goes from the bell scale to the decibel scale. And what we have is that this is our, common logarithm, the Briggsian log, the standard log log. That's just the log button on your calculator kind of log. And I always write in the base because I like to write in the base. I'm just weird like that, I guess. I don't know. Okay. I told you that one of the ways to tell, be careful between the intensity and the intensity level was to look at your units. This is kind of like how we could tell the difference between the alpha angular acceleration and the linear accelerations. The units tell you the difference. Or back in chapter 2, how you could tell the difference between an acceleration and a velocity. When you first started, they're easy to mix up. And if you look at the units, they're easy to sort. And so that's what we want to do. The units are going to be our, friends. And so the SI units of the intensity level are the decibels. And then the units of the intensity are these ones here, are watts per meter squared, power per area kind of things. Okay. So there we go. And so what we want to do is I want to make sure we can use the decibel equation to begin with. Not everybody's really friends with logarithms. And so I at least want to kind of have a discussion about how these things go. And so just let's talk about logarithms in general. And so then what you get is that when we look at something like, log of 100, okay, then what that asks is to what power do you raise the base, which in this case, they suppress the base. It's a 10, so to what power do you raise the base to get the value in the argument of the function? So this is our, where the base goes. And then the quantity in the parentheses, this is your argument of your function. It's what you put into the function. It's the input value. And so when we do these logarithms, what we're asking here is to what power do you raise the base get the value that you put into the argument of the function, of the logarithmic function, but I'm just going to write function. Okay. And so then what we get here is we can rewrite this as being our, log base 10, the unwritten 10. And then we can rewrite 100 as just, 10 squared, or 10 to the second power. And so then you ask, to what power do you raise 10 in order to get 10 to the 2? And the answer is just simply going to be what? Yeah, 2. So logarithms give you the powers, or the orders of magnitude is essentially what you get. So log base 10 of x will give you the power of 10. Okay, it's going to give you the power of 10. So that's kind of what they do.